Okay, so we're going to discuss charged particle beams based off of our last segment. So we're going to read it and discuss it in more detail. Charged particle beam. So a charged particle beam is just a bolt of electricity. A charged particle beam is used to bunch things, and we're going to get into bunching later in this segment. So let's continue to read. A charged particle beam is a spatially localized group of electrically charged particles that have approximately the same position, kinetic energy, resulting in the same velocity and direction. So electrically charged particles are just particles. Electricity is made of particles. And that's pretty much it for that. It's really simple. So let's continue to read. The kinetic energies of the particles are much larger than the energies of particles at ambient temperature. So this thing is hot. It's saying that the kinetic energies are much larger. And so this thing is going to be moving fast, and it's going to be moving rapid, and it's going to be hot. The high energy and directionality of charged particle beams make them useful for many applications in particle physics. See particle beam applications in electron beam technology. So it says right here that they're useful for many applications in particle physics. You know, bunching things is a part of particle physics. And we're going to get into bunching later. We're bringing things to reality from a computer and a lot of other things. This is the power of a charged particle beam. So let's continue. Such beams can be split into two main classes. So now we're getting into bunching. Number one, unbunched beams, coasting beams, or DC beams, which have no longitudinal substructure in the direction of beam motion. So an unbunched beam is like the electricity that's used to power your refrigerator and your stove, you know, power your lights in your house, the electricity that comes from the generator. Those are unbunched beams. Those have no longitudinal substructure in the direction of beam motion. They have no beam motion. They have no direction of beam motion. They have beam motion. They just don't have a direction of beam motion. Number two, bunch beams, in which the particles are distributed into pulses, bunches of particles. Bunch beams are most common in modern facilities, since the most modern particles accelerators require bunch beams for acceleration. So this is what we're looking for. Bunch beams. Bunch beams are what are going to get us our results. So bunching is a process of cells collecting, and cells collecting is how humans are born. So when the sperm fertilizes the egg, the cells collect and create a human being. The cells multiply and collect, and that's a form of collection when they multiply and collect. And another aspect of collection is bunching. So this is another term used for collection when cells collect. This is cell collection. So this is when cells collect. So we want the beam to be bunched. We want the particles to be distributed into pulses, bunches of particles. And bunch beams are most common in modern facilities. As you can see, that's a big clue. Bunch beams are most common in modern facilities, since the most modern particle accelerators require bunch beams for acceleration. So the most modern particle accelerators require bunch beams for acceleration. If you read on the news, you can see that scientists and labs are trying to use photon beams and photon cannons. They're taking photon cannons and colliding photons. I think that this is a more practical application for the future than colliding photons. Bunch beams are going to give us the results we want, and I'll teach you more about it. You can create things on something sort of akin to a supercomputer, and you can bunch things into existence with the device. You have to invent a device that can bunch things, and it's very easy. You can just use an electric generator to bunch things. Assuming a normal distribution of particle positions and impulses, a charged particle beam or a bunch of the beam is characterized by, now we're getting into some very important topics. So a charged particle beam or a bunch of the beam is characterized by the species of particle, e.g. electrons, protons, or atomic nuclei. So what we're going to be working with is electrons, because once again, like we said earlier, the charged particle beam is just a bolt of electricity. So we're going to be working with electrons. We're making electron beams. Next bullet point. The mean energy of the particles often expressed in electron volts, typically keV to GeV. Now, electron volts is a unit of measurement, which is keV to GeV. That's the unit of measurement you need in order to get the proper charged particle beam. The average particle current, often expressed in amperes. Now, this is the particle current. This is how the electricity moves. It kind of moves in a wavelength-like structure, and it's often expressed in amperes. The particle beam size, often using the so-called B function. And I wonder how big of a particle beam you would need in order to bunch things. Bunching things is just bringing things to reality. Like, you could bunch people if you wanted to. That's how cool this is. You could bunch animals. You could bunch cartoon characters from shows. You could bunch magic. What we're looking to do is bunch magic into the real world. The beam emittance, a measure of the area occupied by the beam in one of several phase spaces. So that's just the area occupied by the beam, how much area you're going to be using in order to bunch the object into existence. So we're bunching objects into existence. That's the most important thing I want you to understand. We're bunching objects into existence. These parameters can be expressed in various ways. For example, the current and beam size can be combined into the current density. So that's how dense the current is. So when it's more dense, it's going to be moving more like this jolt of electricity. And the current and energy, or beam voltage, V, can be combined into the perveyance. K equals I multiplied by V to the -3/2 power. And this is the formula for the current and energy. So it's just current and energy. That's exactly what you need in order to have a bolt of electricity, in order to create a charged particle beam. It says it right there, current and energy. So you have energy, which is the actual bolt of electricity. Then you have its current. And so once again, we're working with bunch beams, and bunch beams have a more directed current. They have more direction, like we said earlier. Number 1, on bunch beams, coasting beams or DC beams, which have no longitudinal substructure in the direction of beam motion. So it has no direction of beam motion. Number 2, bunch beams, in which the particles are distributed into pulsed bunches of particles. Bunch beams are most common in modern facilities since the most modern particle accelerators require bunch beams for acceleration. Now, these ones have longitudinal substructure in the direction of beam motion. Bunch beams do. Number 2 does. And that's what we're going to be working with. The charged particle beams that can be manipulated in particle accelerators can be subdivided into electron beams, ion beams, and proton beams. So in labs, they're working with particle accelerators, and you can use electron beams inside of particle accelerators to create charged particle beams that can bunch objects in surreal life. Common types: electron beam or cathode rays, such as in a scanning electron microscope, or in accelerators such as the Large Electron Positron Collider or synchrotron light sources. Once again, we're working with electron beams, and that's exactly what we want. And you see, it can be used for other applications as well. You know, it can be used in scanning electron microscopes. It's used in large electron positron colliders and synchrotron light sources. So it's used for light too. It's used for a lot of things. You know, electron beams are also, once again, the beams to power your household appliances. And you know, that's what we're going to be working with, is electron beams. Proton beams, such as the beams used in proton therapy at colliders such as the Tevatron and the Large Hadron Collider, or for proton beam writing and lithography. Now, this is another beam, but we're not going to be using this beam because these beams are not directed towards bunching things into existence. Ion beams, such as at the Relativistic Heavy Ion Collider or the under construction facility for rare isotope beams. So once again, this is another beam that we're not going to really be working with, but these are beams that can be manipulated inside particle accelerators. As you can see, the under construction facility for rare isotope beams. So they're making new facilities under construction. These facilities are very new, and this is a new science that even scientists don't know about yet. I had to do a lot of research in order to find out this stuff, and I'm just bringing it to you, and I want you to use it. So this is how we're going to be bringing magic to the real world. And this is going to be a revolutionary science for years to come, for generations to come. And I just wanted to get you hip to what a charged particle beam is and how it's going to impact our future for decades to come. Thank you and have a nice day.